All right, hello. Today we start chapter 6. Beginning on page 430. Recall that your chapter 5 homework at MyMathLab has been assigned and is open for completion. Okay, we are multiplying and simplifying rational expressions. Well, rational expressions. Do you remember our definition of a rational number? Back in chapter 1, probably. Let me see what I can do. Much better, thank you. Rational numbers. Do you remember that a rational number is the quotient of integers? So when we were defining our whole numbers and our counting numbers and our integers and our rational numbers and finally our real number set, rational numbers are a quotient of integers. So quotient means what? Right, our answer when we divide. It's the answer when we divide. Integers, A over B. A and B are both integers. But B cannot be equal to division. Whenever we're dividing, we always restrict the denominator. We cannot divide by 0. Division by 0 is undefined. So as long as your denominator is not 0, then we have our definition for a rational number. So a rational number, let's see an integer, 1 over 2. 1 is an integer, 2 is an integer, so that's a rational number. How about 5? That's your whole number, counting number 5. Does it qualify as a rational number? Well, there's an integer in the numerator. What about the denominator? Over 1. Technically, usually, we don't go around writing our whole numbers 1, 7, 17, 23 over 1. But there's times when we need to convert to its relational, rational number format so we can solve a problem. Let's see, 3 over 4. The numerator is an integer, the denominator is an integer, and the denominator is not equal to 0. Okay, well then we are going to be manipulating rational expressions. And rational expressions are quotients of polynomials. So we could have x over 6, maybe 5 over x plus 2, t squared plus 3t minus 10 all over 7t squared minus 4. So we're looking at a polynomial divided by a polynomial where, again, the denominator cannot equal 0. So we say we need to restrict or prevent the denominator from taking on a value of 0. Okay, so in this example, we have a binomial divided by a binomial. So we're looking at the quotient of polynomials, but we want to restrict the denominator. We cannot let the denominator take on a value of 0. And the denominator is x plus 2 cannot be equal to 0. So let's see, x cannot be equal to a -2, adding a -2 to both sides. What happens if x is -2? -2 plus 2 would be 0, causing our denominator to go to 0, and we need to restrict that, prevent that from happening. Division by 0 is undefined. Questions? Find all numbers for which the rational expression is not defined. Okay, common directions. All right, I have 16 over x minus 3. So I have a rational expression, but I need to protect the denominator. So the denominator, x minus 3, cannot be equal to 0. Exchange subtraction to addition, add the opposite. I'm going to add the opposite of -3 to both sides, which is +3. That goes to 0, solving for x equals 3. So x cannot equal 3, or my denominator would take on a value of 0. If x is 3, 3 plus a -3 is 0, protecting or restricting your denominator. Two x minus 7 divided by x squared plus 5x minus 24. Find all numbers for which the rational expression is not defined. We're thinking about checking this denominator and protecting it from going to 0. So can I factor that? Looks like x squared plus 5x minus 24, ax squared plus bx plus c, a trinomial that we could factor. There's no greatest common factor, so I'm going to use my factor table. Factor pairs of a -24 whose sum is coefficient on the middle term. Middle term is positive, so 8 times a -3. 8 times a -3 is -24. That'd be +5 when I add my factors. So I can factor this as x plus 8 times x minus 3. I'm going to use my principle of 0 product rule and set your factors equal to 0. If either of those factors is equal to 0, my denominator would be 0, right? So I need to protect or restrict so that doesn't occur. So x equals a -8 or x equals a +3 to set it equal to 0. So I'm going to make sure that x does not equal a -8 or x does not equal 3. Otherwise, all values for our real numbers could be substituted for x and we could solve this rational expression. X plus 5 divided by 8. Okay, solving for numbers that make this rational expression not valid. Well, I have a constant in the denominator's position, so it will constantly remain something other than 0. So this is a rational expression that remains valid for all real numbers. It's the denominator that we're concerned about, of denominator taking on a value of 0. Now we're asked to simplify. 6a plus 12 divided by 7a plus 14. Well, simplifying, we're going to factor and look for other names for 1. So factoring is their greatest common factor. Kind of always our first step. Greatest common factor. Well, in the numerator, it looks like 6. 6, so I'm going to use the distributive property in reverse. 6 times what would give me 6a? Pick up your sign, and 6 times what would give me 12? In the denominator, 7 looks like greatest common factor. 7 times what would give me 7a? And 7 times what would give me 14? Okay, simplifying. So now we're looking for other names for 1. Well, everything is factored. That has to be, we can simplify by looking for another name for 1 as long as it's all multiplication. And it is. So here I have another name for 1, leaving 6/7. Now, as we're simplifying, we understand that we are not going to let our denominator take on a value of 0. And now we can proceed. So we are understanding that we're manipulating these rational expressions, knowing that we would never let a denominator take on a value of 0. We know how to protect a denominator from taking on a value of 0 now. Now we're accepting that we would not allow that to happen, so we're going on to solve rational expressions and simplify. Okay? So section A is over, done. We know we will restrict and protect our denominator from taking on a value of 0. Otherwise, we're going to move ahead and begin to simplify rational expressions. So simplify 6x squared plus 4x all over 2x squared plus 2x. Simplify. We look to factor and solve for other names for 1. So factoring, we always look for that greatest common factor. In the numerator, it looks like we have a factor of 2 at least. 2, that's even, and that's even for my coefficients. But there's a factor of x in both terms also, right? I'm going to factor out 2x. And then use a distributive property in reverse. 2x times what will give me 6x squared? 3x. Pick up your sign. And distribute 2x times what will give you 4x? 2. In the denominator, same thing. We're factoring. I look at my factoring a polynomial checkoff list, and we should look for a greatest common factor first. Do you see a greatest common factor in these two terms? There's a 2, and there is an x. So the distributive property in reverse, 2x times what will give you 2x squared? 2x times what gives us 2x squared? see an x? Pick up your sign. And 2x times what will give me 2x? 2x times what will give me 2x? 1. Okay, yeah, thank you. And now we look for other names for 1. 2x over 2x is another name for 1, leaving 3x plus 2 over x plus 1. Simplify. X squared plus 3x plus 2 all over x squared minus 1. So in the numerator, I'm going to get out my blue card. There's no greatest common factor, but remember, it is of our form pattern, ax squared plus bx plus c. So I expect I can factor it as a product of 2 binomials. So I'm going to use my factor table and factor the constant 2 and find factor pairs whose sum is plus 3. So I guess factoring 2 is 1 times 2. I'm going to factor this as x plus 2 times x plus 1. In the denominator, I'm looking to factor this. Greatest common factor, no. There's 2 terms. Is it the difference of 2 squares? I think so. 1 times 1 times 1 times 1, 1 times 1, 1 squared is 1. So that's the difference of 2 squares. We'll factor that as x minus 1 times the quantity x plus 1. The product of the sum and a difference. Here's a squared minus b squared, and it factors as a plus b times the quantity a minus b. The middle terms cancel out because they're opposite signs. Questions? All right, we've factored. So now we look for other names for 1. And that leaves x plus 2 over x minus 1. We're still simplifying. The opposite of the polynomial a minus b is that correct? The opposite, I'm going to change the sign of every term in this polynomial. So this was a negative, it's now positive. This was positive, it's now negative. Kind of skipped a couple steps, but this is a relationship you should think of. So opposites. Okay, so we're supposed to simplify. X minus 4 over 4 minus x. But when we're simplifying, we look to factor first, and then we can look for other names for 1. We need to factor something times something. We can't simplify when we're adding and subtracting and dividing. We can simplify finding another name for 1 when it's all multiplication. So I see an x and a 4 and a 4 and an x. That makes me think, could I factor a -1 times 4 minus x? a negative 1 times 4 minus x is, I'm going to change the sign of each of these terms, x minus 4, which is my numerator. So let's factor. Factoring the numerator, I have 1 times x minus 4. That's factored, something times something. And in the denominator, I'm going to factor this as a negative 1 times 4 x minus 4. Oh. Yeah. A negative 1 times x would be my negative x. And a negative 1 times a negative 4 is positive 4. I haven't changed the value, I just factored out a negative 1, which changes the sign of each term. Everything's factored. This is all something times something, something times something, so I can look for another name for 1. X minus 4 over x minus 4 is another name for 1. And 1 over a negative 1 is negative 1. Factoring out a factor of negative 1. And especially when you see the terms x and a 4 and a 4 and an x, it's kind of a clue. Look for that strategy of factoring out a negative 1. That's on page 434. There's a couple of other examples of factoring out a negative 1. Simplify x squared plus 6x plus 9 divided by x squared minus 4 times x minus 2 over x plus 3. And simplify. Well, to simplify, we know we need to factor. And then we can look for other names for 1. It has to be factored. Here we're adding terms and we're multiplying, but we're adding some and subtracting some terms in the numerator and the denominator. It has to be all factored. So this looks like ax squared plus bx plus c. So we expect we could factor that as the product of two binomials. Is the first term a perfect square? Yes. Is the last term a perfect square? Yes, so we can factor that as x plus 3 times x plus 3. Perfect square trinomial. In the denominator, there's no greatest common factor. Could that be a two-termed difference of two squares? I'm going to factor that as x minus 2 times the quantity x plus 2. The middle terms cancel out. They're opposite signs. Times, looks like x minus 2 over x plus 3. Now this is all multiplication, right? Something times something times something in the numerator. So I can rewrite this as x plus 3 times x plus 3 times x minus 2 in the numerator. In the denominator, x minus 2 times x plus 2 times x plus 3. It's all multiplication. So now I can begin to look for other names for 1. Looks like I have an x plus 3 divided by an x plus 3. And here's an x minus 2 divided by x minus 2. What's left in the numerator? X plus 3. What's left in the denominator? X plus 2. Okay, we're given x plus 4 divided by x squared minus 3x minus 10. Now, we know with our relational expressions that the denominator cannot take on a value of 0. So when this trinomial is equal to 0, this relational expression is undefined. So we need to factor and set our factors equal to 0 and determine when will that denominator be equal to 0 and then say it cannot take on those values. So factoring. 10 is not a perfect square, so we have to go to our factor table, find factor pairs of negative 10, whose sum is a negative 3. Negative 5 times 2 is a negative 10. Adding negative 5 plus 2, I get a negative 3. X plus 4 divided by, I'm going to factor x minus 5 times x plus 2. So I can't let either or both of these factors take on a value of 0. X minus 5 cannot equal 0, or x plus 2 cannot equal 0. Or my denominator would be undefined. So x cannot equal 5, or x cannot equal a negative 2. So factoring is playing a huge part in solving our rational expressions. Questions? Let's just test this. X plus 4 divided by x squared minus 3x minus 10 when x equals 5. So I have 5 plus 4 in the numerator, and then the denominator I have 5 squared minus 3 times 5 minus 10. That's 9 over 25 minus 3 times 5 is 15 minus 10. 9 over 25, that's a negative 15 plus a negative 10 would be a negative 25. 9 over 0, oops. So that's why x cannot equal 5. And you can check by substituting your negative 2. Okay, when we multiply fractions, 2/3 times 5 over 11. Multiplication of fractions is a piece of cake. We multiply the numerators, multiply the denominators, and simplify if we can. Multiplication of fractions is a piece of cake. Multiply the numerators, multiply the denominators. Of course, we simplify if we can. Well, multiplication of rational expressions. Five a cubed over 4 times 6 over 5a. Multiplication of rational expressions, it looks like it's fractional form. I have a monomial in the numerator and I have a constant in the denominator. Maybe I'll have a binomial in the numerator over a trinomial in the denominator, but it's in fractional form. So multiplication is a piece of cake. Multiply the numerators. I'll have 5 times 6 would be 30 a cubed over 4 times 5 is 20a. And simplify if we can. Let's see, 10 goes into 30 and 20 evenly for 3 halves. And your rules for exponents, this is a to the first. So I'm going to subtract the denominator's exponent from the same base's exponent in the numerator. And I'll get a squared. Or expand and look for other names for 1. 10, 10, and a leaves 3a squared in the numerator and 2 in the denominator. Remember dividing fractions. Our rule for division of fractions. Change division to multiplication and multiply by the reciprocal. Reciprocal, we reciprocal, we reflipical, and keep the sign. Number 7/8 times what equals positive 1 is the definition of our reciprocal. So 7/8 times 8/7. Reciprocal, flip it, 56 over 56. That's right, isn't it? 7 times 8 is positive 1. But how about a negative 7/8 times what equals positive 1? Well, I know I'm going to flip it, but that would be a negative 1. So I need to keep the sign. A negative times negative is positive. I'll have 56 over 56 equals positive 1. Definition of a reciprocal includes managing the sign. Okay, well now we know how to multiply fractions. Multiplication of fractions is a piece of cake. Multiply the numerators, multiply the denominators, and simplify if you can. (15 over 8a squared divided by 9 over 8a. Well, that looks like a numerator over a denominator divided by a numerator over a denominator, but I do have monomials involved this time, or rational expressions. So I'm going to change division to multiplication and multiply by the reciprocal. Well, now I can look to simplify by finding other names for 1. If you're okay with cancellation. 3 goes into 9. How many times? And 3 goes into 15. How many times? 8a squared goes into 8a. How many times? Well, 8 goes into 8 once, right? And I'm going to end up with an a in the denominator. Cancel out the a in the numerator. So looks like in the numerator, all I have left is 5. In the denominator, I have an a times a 3 for 3a. If you don't care for cancellation, because look how sloppy it gets. We had 15 over 8a squared times 8a over 9. Well, 15 is 3 times 5. This is all multiplication times 8 times a, all over 8a times a times 3 times 3. So expand and factor using your prime factorizations. 3 goes into 3 once. 8 goes into 8 once. A goes into a once. In the numerator, we have 5. In the denominator, I have a times 3, which is 3a. Two over x divided by 3 over x. Division, I'm going to change division to multiplication and multiply by the reciprocal. So it's all multiplication. I have 2x over 3x. Looking for other names for 1. X over x is another name for 1, leaving 2/3. Four over x squared minus 7x divided by 28x over x squared minus 49. Division. So I'm going to rewrite this as 4 over x squared minus 7x times, change division to multiplication and multiply by the reciprocal. So now I want to factor x squared minus 7x. Factoring, we're going to look for that greatest common factor first. Looks like there's a common factor of x. Times, in the numerator, x squared minus 4, be 9, 49, x squared minus 49. There's no greatest common factor, but 2 terms is the difference of 2 squares. 49 is 7 squared, so I'm going to factor that as x minus 7 times the quantity x plus 7, all over 28x. Now that is all multiplication. Here I had multiplication, but I was adding and or subtracting terms. Now I'm multiplying all terms in the numerator, multiplying all terms in the denominator. 4 times x minus 7 times x plus 7 all over x times x minus 7 times 28x. 4 goes into 4 once, and 4 goes into 28 7 times. The quantity x minus 7 goes into the quantity x minus 7 once. In the numerator, that leaves x plus 7. In the denominator, it looks like 7 times x times x, 7x squared. Here's an x, there's an x, 7. X plus 7 over 7x squared. X squared minus 2x minus 3 divided by x squared minus 4 divided by x plus 1 all over x plus 5. Well, I have rational expressions in division. I'm going to change division to multiplication and multiply by the reciprocal. Now I have some adding and subtracting going on. I can't look for other names for 1 yet, but I can factor. Look to factor. This is a trinomial. With my factor table, I can factor this as x minus 3 times x plus 1. In the denominator, I'm looking to factor. Is that the difference of 2 squares? 4 is a perfect square. X minus 2 times the quantity x plus 2 times x plus 5 over x plus 1. Now this is all multiplication, so I can rewrite this in my numerator, and my denominator it's all multiplication. It's a binomial times a binomial times a binomial. So I can look to simplify by looking for other names for 1. X minus 3, x plus 1, x plus 5. Looks like I have left x minus 3 times x plus 5 in the numerator, and in the denominator, x minus 2 times the quantity x plus 2. I have handouts for your rubric, for your graphing project. If anyone wants to pick one up, otherwise I did email an attachment to everyone. Reminder that that is due at 3 p.m. on 10/7, which is this week. And it's published. And chapter 6, we cover limited amount of information. So your chapter 6 test is open at my math lab, test and homework. Let's start with homework. Your chapter 6 homework is open at my math lab. It's due on October 11th at noon. And it covers topics 6.1, 6.2, which we covered today. We skipped 6.3, 6.4, and 6.5. So 6.5 is halfway through chapter 6. So material halfway through chapter 6, but we skipped section 6.3. And your tests are also open at my math lab, due at noon on 10/11. Topics 6.1, 6.2, 6.4, and 6.5. And I'll be publishing this to D2L as well. All right, so we skip section 6.3. Moving on to 6.4, we're going to start adding rational expressions tomorrow.